We are in this kind of section of the course where we're developing a bunch of rules to get closed forms quickly of certain types of accumulation functions. So these are very common accumulation functions, and we're going to find more. For these very common accumulation functions, we're building rules for the rate of change function that allow us to get the closed form rate of change very quickly, right? But we know that it's all of these are based on the open form. And in deriving these, we always use the open form to get started to figure out what the closed form rule is. So we're kind of coming up in the next week or two with this very algebraic intensive kind of part of the course where these rules are going to get more complicated in an algebraic way. And so the quiz is to try to keep us from kind of forgetting all the meanings, right? So the quiz this week is that at the same time we want to maintain all these the meanings and the origins and the big picture of what we're doing, okay? So the quiz doesn't have any of this, the algebra side of it. You're deriving one of them. You're deriving one of these rules, but beyond that, we're not using the closed form rules in rapid fire. Rather, we're kind of, again, talking about big picture representations and what the symbols mean, okay? So any questions on what we have so far? So we're going to keep going on building more of these rules. Let's see. There we go. Any questions before we go on to the next rule that we're going to develop? Okay, so here we go. Really? Okay, well, I don't know why that does that, but so we have seen an example of a composite function this semester. What was the example of the composite function that we've seen? Where am I? Okay, so what is a composite function, and what we've seen an example of it this semester? What was it? I know Chloe knows. Anybody else? Nicholas.
So like two functions, or one function is a result of two functions doing something. So. Okay,
so composite function has to do with combining two functions in some way. How is it that we combine two functions in a composite function? Chloe, you want to answer that question? So, what's that? No. So my new question is, just in general, a composite function combines two functions in a certain way. How does it do that?
So one function becomes the input of another function.
Okay, right. So we go through the process of the first function, and we take that output, and what do? It makes it the input of another function. So then where are we seeing that? Okay, step function. So what was the first function? What was the first function in that process, whose output then we stuck into another function to go through a second process?
Left
Christian.
or right or mid of X.
Okay, that was the first or the second?
And the first.
Yeah, so left, right? What went into the left function? Which x value?
Some point on the x-axis.
Any current x value, right? We put it into left, and what came out?
New x value.
Okay, another x value. Which one?
Jeez.
What's going on with this? Sorry, I don't know what happened to the slide. It's all messed up. All right, so what went in? X went in. Shane is getting a kick out of it. Okay, so X went in, and what came out? Another X. Which X? The X at the left side of the current interval. And then what do we do with that left X? Right, we put it, okay, so that's left X. We put it into our exact rate function, and then what came out? The rate at the left side so that that whole interval, no matter what x value in that interval we put in, we always got the same rate at the rate corresponding to the rate at the left side. Okay, and so, oh, now it wants to work. No, I guess not. Anyway. So this composite process was, let's see, left of r of x or r of left of x? So left of r of x or r of left of x? So notation here. What notation represents this process? First or second?
Second.
Yeah, what comes first? Because first we put x into left, and then and then that represents the output, and then we put that output into r. Okay, so that's the idea of a composite function. So what about we have a composite function, say, what about the rate of change of a composite function? Can we get a closed form rule for the rate of change of a composite function? Okay. All right, so first, for practice, first explain the processes represented by g of f of x and draw an illustration of that process. So it's a little practice here for composition. So explain the process g of f of x.
So like the
And-
one.
Nope, just like the last screen was a representation of, just a representation of the composition, nothing to do with rate of change. Okay, which process is first? Shannon? So this one you want to be f? And x goes into that? And what comes out? F of x? And someone take it over from there. Mackenzie, what happens then?
And then f of x is going to go into the function with the box that you drew, where g is in there.
So this process is, which function is this?
That's going to be like the g of f of
This is
x.
the g function. So I'm going to take f and I'm going to put that into g. And what comes out?
The g f of x.
That's right. Is that what you guys did? Everyone else? Make sense? Okay. So the following functions can be thought of or can be seen from the perspective of a composite function, g of f of x. So I want you to identify what is g and what is f in each case. All right, but we're going to, let's see. I'm going to just nix this one, okay? This one's a little different. So just those four. So maybe let's do this one together. So how can we see this h of x as g of f of x? So what we're trying to do is kind of pull this apart and say what would the f function be and what would the g function be such that if you had g of f of x, it would be this h, the square root of x cubed minus 5. Brent, any ideas?
I think you could be, no.
So what we want to see is one function, how is this one function rule kind of plugged into another? Can you see it?
So could you make f of x like x cubed minus 5 and then g whatever f of x is to the 1/2.
Well, so g doesn't know anything about f. So we're going to take f and we're going to make it the input into g. So what would the g function be that would result in this? Square root of?
f of x.
So it doesn't know anything about f. X, yeah. Does it make sense? So now if you set up g of f of x, you would take the output of f, right? As you say, you put x into f, take the output is x cubed minus 5, and that becomes the input into g. And if you did that, you would get the square root of x cubed minus 5. Does it make sense? Okay, so this is a little small. This is e to the 3x to the 8th. So try these other three. See if you can write each of these p, v, and q as composite functions, all of them g of f. So what is f and what is g? Give it a shot. Go. And then, so compare with the person around you, next to you. See if you guys are coming up with the same thing. And I take one lap for questions. Okay, Stephen, how about this first one, p of x? Did you come up with what f and g might be?
F goes to the f of x is 3x to the 8th.
3x to the 8th?
G of x is 3 to the x.
Say it again, g of x is?
E to the x.
E to the x. What do you guys think? Does it work? Yeah. Okay, how about v of x? Ryan?
Let me find here. F of x is natural log of x. And then g of x is 1 over x.
How do you do? Does it work? Ariana, did you get this last one? Okay. Do you want to take a shot at this now on the fly, or do you want to pass? So f of x is what? F of x is the one that x goes into first. 1 over x. Sine of x. Any questions on those? Did you get them? Okay, so let's talk about now, so what about, say, the rate of change of h of x? Let's look at this. So what is the overall structure of h of x? In totality, what kind of function is that? Square root, right? It's the square root of something. And what did we say? The rate of change. So then what did we say the rate? We did this last time. What's our closed form rule for h prime of x? 1 over 2 times square root. It's just now that inside we have, instead of x, what do we have? Q minus 5. Okay, and so then we all down here, likewise, we'd have x cubed minus 5. So, according to our closed form rule for square root of x, would you agree that that closed form rule would indicate this rate of change function? Is that fair?
Yeah.
How can we check it?
Right.
How can we check that? So we want to check to see if this is indeed the rate of change function for h of x. How can we do it? Okay, so you want like an algebraic kind of? Like do the open, what do you mean when you say plug it into the open? What do you mean?
The f of x plus h minus f of x over.
Okay, so we could write the open form of that. Okay, but with the cube and then the square root, it's going to get really ugly really fast. So yeah, that's one possibility. So we could try to set up the open form and see if we can simplify it to look like this. But I'm just kind of warning you ahead of time. That's going to be a mess. Okay, it's going to be hard. So what's another way we could check to see if this is our rate of change function for this?
Graph it.
What's that?
Can we graph it?
Graph it. What do you want to graph?
We can graph these rate of change function against the original function.
So what's our original function? So I called it h of x. Square root of
X cubed minus 5.
x cubed minus 5. Is that right? Okay, and then we came up with our hypothesis of, so we'll just graph that first. And we'll make that blue. Blue is our original function. So maybe we should, okay, there we go. All right, how are we going to check our, so we're asking if, what did we come up with? So let's just call it, I don't know, doesn't matter. We'll just call it G is our, right, yeah, so K of X is good. K of X, it's great. Okay, so K of X is, we think maybe it's 1 over 2 square root of x cubed minus 5. And then we want to graph that. Let's make that red. Okay, so they're not the same. Observations, conclusions about what, so what did I do? I graphed h of x, and I graphed our conjectured rate of change function. Aaron?
I'm not sure, but just looking at it, it's supposed to like starts off looking quite similar, but because it's a square root, because when you start, but the red goes down, it starts and it hits the x-axis of 0, and it kind of has to stay along that line in order for it to stay true. But if it couldn't, it probably would have continued on. Maybe like exactly your opposite.
Okay. So you're kind of looking at these two graphs and trying to see what's going on. James?
I hate graphing. Just to say that to start with, couldn't you break it down using what you just showed us into 2 different functions and verify those 2 functions separately together?
Are you talking about doing the open form?
Yeah, you use the open form, but instead of doing the whole thing with the square root of the cubes, break it down into the open form of f of x, the open form of g of x, I guess.
So if we expand the open form of this function h of x, the open form rate of change, it's a really hard algebra problem.
Well, yeah, if you leave it as is, but if you break it down into x cubed minus 5 for one of them, and the square root of x is the other one, you get the open form of those 2 instead. Wouldn't that be a lot easier?
But what are you saying is the rate of change of that?
I would have to work it out.
Yeah.
I'm
So
just asking in theory before doing all the work.
If you could break up the square
Yeah.
root in the actual
So do the open form of x cubed minus 5 and then it's at the
I
square
feel
root.
like you can combine the rate of change of f of x and g of x.
Yeah.
That's the question.
So your hypothesis is that this is your hypothesis. You're saying that it's would be 1 over 2 radical 3x squared. That's what you're saying. That's your hypothesis for the rate, because you're going to do 1 over radical and you're going to plug in. Okay. And so, how are you going to check it without graphing then?
I would break up the, in the original formula we had written x cubed minus 5 as f of x and then g of f of x being square root of x. So I do the open form for x cubed minus 5 and then plug that into the open form of the square root of x. I just want to know if that's possible.
I'd have to take more time to think about what you're saying, but I don't. It's not going to work.
Okay.
It's not going to work. So we're gonna go with a graph approach because it's fast. Graph approach is fast. So Ross.
That h is an accumulation and k is a rate.
Okay, he's saying that H is the accumulation, the blue one's accumulation, and red is rate. So we're trying to compare apples and oranges here. Is that what you're gonna say?
Right off the bat, I just think that you can tell that it's not it because like the red is the
No. So you're trying to compare these. He's saying these are apples and oranges. So before you go any further, he's saying these are apples and oranges. This is an accumulation function, and this is a rate function. So why would you compare them in the first place?
because couldn't you tell how it's accumulating from the rate and like the
Oh, I see.
the rate function is staying
Okay.
on the stack.
But so we can do, okay, right, so yes. So you're looking at what would the rate function be like based on the way this accumulation looks. Okay, that's okay, but so let's get it precisely by looking at graphs. So how do we want to change what we're doing, Kevin?
Well, I just want to talk about the graph more. I'm not gonna answer your question. You want to pick up something else, or?
Yeah, we need to get moving. So we don't want to spin our wheels too much here, right?
Can we, instead of trying to expand out the rate of x3 minus 5, can you just take the, can you define a rate function and just call it h of x? Because you have h of x defined. So can you do r of x and then do the open form of h of x?
Okay, right. So we don't want to graph the accumulation function. You see, we don't care about the blue one. We want to take our conjectured rate of change function against what? What do we want to compare it to? The actual rate function. And what's our trusted form for rate of change? Open form. So what is that? That's going to be r of x. And so how am I going to write what r of x is? Oh, I called it h again. This is so dumb. Well, that was because of the slide. So we're going to change this to g. Sorry. Okay, now this will be better. Okay, now, so how are we going to... Kevin.
It would be the square root of x cubed. No, not x. It would be x plus h cubed minus 5, right?
We've named that g of x, so we can let's use that.
G of x
Yeah.
minus g of x plus h.
G of x plus h.
Minus g of x over h. All over h.
Okay, what about this now? Are we ready to compare them? Why not? H is what? H has to be small. So what do you want h to be? H equals? There we go. Just make h small. And now we're ready to compare. And we're going to make the rate. So the actual rate of our accumulation function is the blue one. And our projected rate is the red one. Right. Y equals r of x. Thank you. And that's going to be in blue, right? How do we do? So, again, our blue is our actual, yeah, that's a little bit of drool there. Got a little calculator drool. All right, so here's our true rate function based on the open form. And then this is our conjectured rate based on just following the rule for the square root. What do we think? Is that right? Why not? Go ahead.
I don't, it's not right, obviously, because of the graph, but the reason it's not right is because we're not taking into account the fact that f of x also changes at a specific rate. So we're only taking into account the rate of change of I believe it's g of x. So in order to find the true rate for k of x, for g of x, I'm sorry, we have to take into account both rates of change.
Right, so that's an excellent point. So and that's where we're going here. So this conjecture only takes into account what? It only takes the square root into account as having a rate of change. But this has a rate of change as well. You see, the x cubed minus 5, it has some rate of change relative to x, and that's not taken into account here. We've got that y value in here, but we don't have whatever its rate is factored into this whole thing. Okay, so good observation. Okay, so we need something else, right? This is not working. This does not work. Just following that closed form square root rule as it is doesn't work as a composite function. Okay, so suppose a function f has a rate of change function r of f. Okay, and that r of f at 6.1 equals 3.8. All right, so what is the meaning of 3.8? Go. Talk to the person next to you. What does that number mean? 3.8. What does it mean?
Whatever x is.
Okay. Yeah, Sean.
X is equal to 6.1.
Okay. All right, so at x equals 6.1, f is changing at a rate of 3.8, is that what you said?
Yep.
With respect to?
Yep.
With respect to what?
X.
X. What am I going to ask? No. It's right, but what am I going to ask? What does that mean? What does that mean? This is the question we've been asking. So yeah, that's kind of the statement of that kind of how we define that number. But what does that mean? Peter.
When x equals 6.1, a tiny change after 6.1,
Okay.
y will change 3.8 times that tiny change.
Someone's learned something in this class. Did you hear what he said? Say it again.
When x equals 6.1,
Okay.
y will change, or change in x with tiny change in x.
Right.
Y will change the 3.8 times that tiny change.
Right. So for around 6.1, for every change in x, y changes how much? 3.8 times as much as whatever change in x you have. Right? It's how x and y are changing together. So if time goes by a little bit, then whatever your changing quantity is going to change 3.8 times as much as the amount of time that went by. Okay? Excellent. This means that if x moves a tiny bit from 6.1, the value of f will change approximately 3.8 times as much. And so why am I saying approximately? What's that?
Because it's changing.
What's it?
The rate.
The rate is the rate for f. We're just assuming it has not changing rate. So as soon as you make that tiny change in x, the rate is a tiny bit different. Okay, so we can use the principle of constant rate of change, but we have to have our really small values of x. Okay. Okay. Ignore this. Okay. So there are two functions, f and g. So the rate of change of f with respect to x at 5 is 5 at 627. And the rate of change of g is 3 at 2714. What is the rate of change of g of f of x with respect to x at x equals 6? So this is our question. What happens in a composite function? What is the rate of change? So in a composite function, where would we begin? What would we start with? In this particular composite function, what would come first? F of x would come first. So as x changes a little bit, how does f change? If x changes a little bit from x equals 6, how does f change? 5 per change in x. 5 times as much as the change in x, right? Okay, so change x by a little bit, and how much does f change? 5 times as much. See that? So if you change x by a little bit, you're going to get this much of a change of f. Okay, so now if f changes this much, how much is g going to change? 3 times what?
3 times of the size of f.
He's saying, so if we have g of f of x and f changes by a little bit, he's saying that g will change 3 times as much as the change of f. Is that right? Yeah, because that's what g with respect to its input is. The rate of change of g with respect to its input is 3 times as much. So for a change of f of that much, so like this, here's the amount of change of f from here to here. G will change 3 times as much as that. So when x changes a little bit, how much does g of f of x change? So for how much does g of f of x change for a little change in x?
15.
15 times as much. Does Zoe agree with that? Yeah, so you see it. So if f changes 3 times as much as x, and then g changes 3 times as much as its input f, then in the end we really have a rate of change of 15 times as much as x changed. Okay, so we change the input by a little bit. The output of g changes 5 times 3 times as much, or 15. So we could say that the change in g of f of x was what? 15. Or first the rate of change of f with respect to x, right? Times, and that was our 5, times the rate of change of g with respect to f, and that was 3 delta x. So I'm saying the change in g. So the change in g is going to be 15 times the change in x. So the 5 came from the rate of change of f with respect to the initial input x, and then the 3 came from the rate of change of g with respect to its input, which its input was the output of f. So does what I wrote there by hand, does that make sense? And so this is our basis for how we find the rate of change for a composite function. This illustration and this, what I wrote here. This is the heart of the matter. Okay, so then, but normally when we end up developing the rule, these are switched. We write this one first, and then we tack this one on second. But in the order of the process, this really comes first. This 5 times the change in x, and then 3 times the change in f. That's really the order of the process. But when writing the rule, conventionally, we do this first, and then we do that. But just know that reading left to right, this is really the order of the process. Any questions on that? Really important. Okay, so that's what I was talking. So here's the order changed. Okay, here's the order changed. This came first. This was our 5. The rate of change of f with respect to x was 5, and then the rate of change of g with respect to its input was 3. So here's how we say those things, right? As we've been practicing, the rate of change of f with respect to x, the rate of change of g with respect to f, and the rate of change of g composed with f with respect to x. Okay, so we could also use the prime. If you use the prime notation, it would be this. That would be the same exactly. You'd say the exact same thing using the prime notation.
How come the prime of
Yeah.
g, or the rate of g with the f of x as input has to be multiplied by the f of x? Like I thought it was already done when it.
This was the first thing in the process. This was our 5. So f changed 5 times as fast as x. And this was our 5. And then g changed 5 times as fast as whatever its input was, and that was the output of f.
But wouldn't that just be like g prime times f?
Not g prime of x. G prime of its input. So see, the input of g is the output of f. So, and then we saw that in the illustration. It wasn't just g prime of x, it was g prime of f, right? Those the big chunks. Yeah, so yeah, it has to be the input into g in our function is f. And so the rate of change of g is taken with respect to its input, which in this case was f, which was those chunks of 5 delta x's. Does that help? Other questions? Okay, so note, so this maybe, is this what you're saying? This is what you wanted?
Well, yeah, because it's like, yeah, it's not right.
You see why it's not right? Because that second part, when we got the 15 little ones, that was made up of the 3 big ones of 5 each. Let's go back and have a drum. So we could look at it later. But so this is the common student error, is that you just take the rate of change of g times, it's not just the rate of change of g times the rate of change of f. The input into g is f, and so that rate of change is with respect to its input, which is f. Okay. Any questions? So that's saying that the input into g has to be f. And so then when we actually apply this rule and we're just immersed in the algebra, this is an important point. That when you're writing the rate of change of g, you have to have that input as f, not x, and not f prime of x. Those are the most common mistake that students want to put. They want to put the rate of change of f in here. But it's just f as it is, because it's how g is changing with respect to f. Okay, so let's go back to our examples, and let's see if we can do this here. So, where was that? Here. Okay, so these are the ones we worked on. So let's do this first one together, and then I'll let you do the others. Okay, so this one, what did we say f and, so we want to know what, we're writing what f h prime is. So our, what did our chain rule say? The rate of change of g with respect to f times the rate of change of f with respect to x? What's up? Are we good? Okay. So what did we have for our f and g? So we said f was originally? X cubed minus 5, and our g was? Square root of x. So we're going to take the rate of change of g with respect to the original function f. So what is that?
Dx squared minus squared.
What's the rate of change of g with respect to the original function f? Okay, yeah, right. It's be 1 over 2 square root of, but now f in here, right? F. So x cubed minus 5. But then, so that was what we tried, right? But now we see that you need, like Chloe said, we need the rate of change of f also, and it just ends up being multiplied on. Because our x gets magnified by the rate of f, and then that gets magnified by the rate of g, you see? So this is actually the first part in that process. So what's the rate of change of f with respect to x? 3x squared. So we can go back to our, let's go back to our rate here today. And now we want to change what? So we've got that, we know the open form is right. So we come back here to k of x, and we change it and add what? Include that part we didn't have. The rate of change of f with respect to x, and now they should match. Right, Christian, that's the thing we should get excited about, not the fact that it can do algebra for us, right? Remember when I showed you the algebra? Y'all were like, it was like, you know, this is the cool thing. So yeah, red plus blue equals purple. They're right on top of each other. Okay, so I want you to practice on these others, except that I have to give you a couple rules here that that we've not derived. So I'm just going to give them to you for time's sake. So so let's just say generically our functions are u. So if u is ln of x, rate of change is 1 over x. If u is sine of x, rate of change is, so we're not, I'm just doing this for time's sake. We didn't have time to derive all these. Cosine x. Some planning issues today. Sine x, okay?
Is that negative sine x?
Yes, negative sine x.
You say we're not going to go, like, we're not going to prove those? Or, so just like right
Not today, anyway. So we're just using those to help us practice this, the closed form for a composite function. So this one we're not doing. So you've got 3 to do, okay? Again, this was e to the 3x to the 8th. I'm going to start taking attendance.
Yeah, so but g of x turns into negative 1 over x. Because 1 over x is equal to x to the 1. So then we take our
G
power.
prime is
It goes to negative 1 x
minus
1 x.
G of x.
Okay, let's crank through these 3. We got 2 minutes. Let's crank them out. Janae, did you make progress on this first one? Tell me. So I set up the rule here. So rate of change of g with respect to f. What would that be? So what's the rate of change of e to the x? That was that very special function we found out last time. It's where the rate of change is the same as the original function. So that's the rate of change, but then it's with respect to f. So we leave that same function plugged in to e to the x. Okay, keep going.
And then the f of x is going to be,
What is that? Tell me what that is.
I mean, the
Okay.
is going to be 24x to the 7th.
The rate of change of f with respect to x, 24x to the 7th. So there it is. All right, and then as you're doing your homework, we don't have time now, use GC to find the open form rate for that and try it against yours. Because as the algebra gets more and more complicated, you're prone to mistakes. You can always trust the open form, right? You can always trust the open form. Whereas, your own arithmetic is prone to error. Okay, so check the open form rate of P against your final answer to see if you got it. So with calculating all these closed form rate of change functions, I'll get emails. Are you going to post the salute answers? No, check it on graphing calculator. You can check it on graphing calculator, right? Okay, so V of x. Volunteer, Christian, or Austin. Let's do Austin.
Alright, for the rate of g of x,
Right.
negative 1 over x squared.
Okay, hold on. Come on, so we can get out here.
Negative 1 over x squared for the rate of g of x.
Okay, so you had x to the minus 1 is your g,
Yeah.
but it's actually ln of x, right? ln of x to the minus 1. And so you're doing the rate of change of g, you said was?
It was negative 1 over x squared.
Negative 1 over, you want x squared?
Yeah.
But it's with respect to f, not with respect to x. Right? That's the rate of change of g with respect to f. So you want negative 1 over ln of x squared. You see? Does that make sense?
No.
Because it's, look right here. It's a rate of change of g with respect to f, not with respect to x. With respect to f.
Okay, that makes more sense.
Okay? And then times?
Is 1 over x.
Right, and I told you here that the rate of change of ln of x was 1 over x. So that would be the rate of change of v with respect to x. Questions on that one? Can you ask a more specific question?
Okay, so how does the g of x become negative 1 over
All right, so if we have something to the negative 1, power rule says negative 1 of that something to the negative 2. And so then I just changed it back into that. So I'm using the power rule. Is it okay?
Yeah.
Cool. Last one. Christian, go.
Alright, so I got, so for the g prime of f of x, I got cosine of 1 over x.
Cosine of, which is the rate of change of g with respect to f, okay?
Times negative 1 over x squared.
It's that same thing again. The rate of change of f, which would be what I just showed Janae.
So it's negative cosine.
If you got a question on the way out, I'll leave this up here. Catch me on the way out.